Hello. Today we will go over graphing exponential growth functions. We will be dealing with another parent function. We're used to those parent functions where f of x equals b to the x. B is some positive number, not 1. When that b is greater than 0, it's growth, and when it's less than 0, it's decay, which we'll see in 7.2. But the general form of the equation is this, where a is not 0, it's some coefficient in front of this b to the x. B is some constant raised to the x. That's why we call it exponential. Our variable is in the exponent, okay? So let's look at the parent graph. We said the parent graph was f of x equals b to the x. All right. B is greater than 1, it's going to be growth. Notice, if x is 0, b to the 0 equals what? Equals 1, doesn't it? So this graph goes through the point 0, 1. All right, if, and I really should just make these an XY chart, shouldn't I? So we kind of see what these look like. So if 0, that's 1. If x is 1, y is b, b to the 1. B is some positive number greater than 1. So we're going to have a point here when x is 1 that we have 1b. All right. If we took let's see what happens in behavior when we go negative. If we take a number like b to the negative 100, that actually means 1 over b to the 100, doesn't it? This is a positive number greater than 1. If we raise it to a large exponent, it becomes very small. So this approaches 0, right? 1 over a very large number is approaching 0. So the exponential graph function looks like this. Growth function looks like this. Okay? You can predict a few points pretty easily. Now, let's try an example where we have an a other than 1. All right, so let's say if we have y equals 1/2 4 to the x. All right, b is the 4, right? A is the 1/2. Let's plot that. I'm going to do a few points. We said when x is 0, 4 to the 0 will be 1, and y in this case will be 1/2, won't it? When x is 1, 4 to the 1 is 4, times 1/2 is 2, and so on. So this graph is 0, 1/2, 1, 2, looks like this. Now, what happens if we have a negative a? You're going to find we have the same thing that happens with our other functions where a is negative. Let's first point out that b in this equation is 5/2, so it's positive and it's greater than 1. A is in that negative 1, so let's make ourselves a little XY table. All right, at 0, 5 over 2 to the 0 is 1. That would be negative 1. At 1, 5 over 2 to the first, and then negative. So this thing is going to be growing negatively, so it looks like this. Here's my 0, negative 1. Here's my 1, negative 5/2. So it's, notice this is reflected. So if we're saying if a is negative, we have a reflection, which is the same thing we had when we talked about absolute value, when we talked about quadratics, which you didn't get to quite yet, when we talked about square roots. If a is negative, it's a reflection. That's a common theme. All right? Now, if we could get a general form of this equation, it's going to have good old h and k's in it. So it's y equals a b raised to the x minus h plus k. And this is right for b greater than 1. Well, guess what? H is our horizontal movement, same as it was with those other graphs. K is our vertical movement. Let's graph one of these. Y equals 4 times 2 to the x minus 1 minus 3. Let's identify some things. Well, A is 4, B is 2, H is 1, and K equals negative 3. So we are going to sketch this, and then we will compare it to the parent. So our graph, remember up here, we want to make the numbers work well for us. So we wanted to start with a 0 up here. So if I do an x of 1, that makes this 2 to the 0, which is 1, times 4 is 4, minus 3 is 1. Let's say we want this to be 0. Oh no, that's what I just did. Sorry. What if we want this to be 1? Then we put a 2 in there. 2 minus 1 is 1. 2 to the 1 is 2, times 4 is 8, minus 3 is 5. So I'm going to graph this. And I have 1, 1, and I have 2, 5. Now let's see what happens as I move negatively. Right? If we go to a very, I'll say large negative number, right? This would become 4 times 1 over 2 to some large number, because that negative would put it in the denominator, minus 3. So this thing, like we said before, is approaching 0. As x gets large negatively, it puts the 2 in the denominator. This is approaching 0. So this is approaching and not hitting 4 times 0 minus 3. So our graph is approaching negative 3. Okay? Let's compare that to the graph. So I'm going to rewrite this. This is 4 times 2, x minus 1. Minus 3. Let's compare that to this same graph where x is 0, or h is 0 and k is 0. That would be this, 4 times 2 to the x. Do our little xy table. When x is 0, y is 4. When x is 1, y is 8. And if x gets really, really, really small negatively, it's starting to look like this. Let's use 100. And that thing's approaching 0, isn't it? So our graph goes through 0, 4, 1, 8, whoops, excuse my drawing. Well, what you see is, look at this, our graph has moved over about 1 unit, right? It moved over 1 unit this way. And it moved down 3 units. H and K have the same meaning that they had with those other graphs. Okay? H is the horizontal movement, K is the vertical movement. Now, you'll also be exposed to an equation that looks like this, where a real life quantity increases by some percentage each year. All right, so let's say we have a problem where, let's see, there were 205,703 computer viruses, viruses, and that's in 1996. During the next 7 years, the number of incidences increased by 92% per year. we want to write a growth function that models the number of these computer virus incidents after 1996. And what we would do there is we're going to call that t is 0. Okay? What you're going to find is this A, when you have these real life situations, is the initial amount of whatever you're talking about. Because if I set t equal to 0, t equal to 0 makes this quantity here equal to 1, doesn't it? So at t equals 0, y actually equals a. So we call that the initial amount or concentration or whatever you're talking about. Depends. Well, in this case, we talked about computer viruses. So we'll say y equals 2573 computer viruses. And it's growing at 92% a year. That's the R raised to the t. Here is how we drew our equation. This could be rewritten, just putting this together. So here is our exponential growth. Notice b in this case is positive and greater than 1. A is non-zero. So we can use this to answer the question about how many incidences were there in 2003. Well, if 1996 is 0, 2003 is t equals 7. So what we would do is say, okay, y, I'm going to do this in 2003, equals 2573, 1.92 to the 7th, right? Which is about 247,485 incidences. Well, what this shows you again is when you're working with a real life situation, this A is the initial amount of whatever you're talking about. Okay? And you'll do some problems for these. Finally, we're going to talk about compound interest. Right? We all want to know how much our bank account will grow. And it looks like this. All right, where R is our rate, our annual rate. Okay, and that's in a as a decimal. We always say a percent, but we write it as a decimal in this equation. N is the number of times per year that were compounded. And A is the amount in the account after T years. Now, this is like the A in the equations we saw earlier. It's the principal amount you're investing. That means the original amount. Because at T equals 0, A equals P. So P is our principal, our initial amount. All right, so I'm going to get rid of this. And I am spelling that right. So let's say I deposited $4,000, that's the initial amount, P, in an account that pays 2.92% annual interest. So as a decimal, that's 0.0292, isn't it? Find the balance after 1 year, T equals 1, if interest is compounded quarterly. Well, how many times a year is quarterly? That's 4, right? So we would say A equals, there's our original amount, 1 plus, and this is obviously going to have to be calculated on your computer. There's my rate over the number of times compounded, and up here again times T. And we would find that we have this much money in our account after 1 year. So this will be an equation that we'll want to use, be pretty good at using. All right, the homework I want you to do is 7.1, page 482. And it's 3 through 21, odd, and then 28 through 30, all. Take a look at these. Now, our next section will be exponential decay, which will follow along a lot of the same things here, but it'll be decay instead. All right, good luck.